Okay, dear students, now comes another question. Again, we are going to add some basic concepts on the principle of mathematical induction. Again, as I tried to explain earlier, you see this principle of mathematical induction is used to prove a mathematical statement written in terms of natural numbers or subsets of natural numbers. Look, here you do have another question. It says, proof using principle of mathematical induction that 6 is a power of n minus 1 is a multiple of 5 for n greater than or equal to 1. Look, dear students, this is a true statement and it involves natural numbers because, as you see, n is greater than or equal to 1, so we are going to consider set of natural numbers greater than or equal to 1 or 1, 2, 3, 4 like that. So look, show that this is true by the principle of mathematical induction. As I tried to explain, first we will try to assume this to be p of a certain what? Variable. Since this is written in terms of n, so let's call this to be p of n. This is done intentionally in order to make my explanation simpler. So look, take p of n to be this one. Look, this is just to say that the statement we are going to prove is assumed to be p of n. Now, as I tried to explain earlier, we do have 3 steps in order to apply, in order to show or prove this statement using principle of mathematical induction. So the first step is to check for the first number. Look, here you are given n to be 1, so let's directly substitute 1 here. So as you're putting 1 in place of n, 6 to the power of 1 minus 1 is going to come, which basically is 5. And 5 is a multiple of 5. Everyone agrees that this is a true statement, so it holds true. What if had it been, you see, failing here? If it fails here, students, we don't need to proceed to the next steps. Rather, we stop here and say that this statement is wrong. But for the time being, what we obtained is right, so we need to keep on. So coming to step 2, now we need to assume that it is true for a certain what? You see, k natural number. Assume that it holds true for up to a certain natural number k. Just to explain this, for instance, if you substitute 2 or number 2 in place of n, 6 squared can come, which actually is 36, and 36 minus 1 is 35. And we know that 35 is a multiple of 5. What will happen if I put 3 here? 6 cubed can come, which actually is 216, and that minus 1 makes 200 what? 15. And we know that 215 is a multiple of 5 again. So for how long are you going to check this? Instead of doing this kind of tedious, you see, approach, what you need to do is assume that this holds true up to a certain what? Natural number k. We don't know this what k exactly, but assume it works true up to a certain what? Natural number k. So what is assumed here is if you are able to show that this also holds true, you see, for the next natural number, that is to say, k plus 1, the statement can be said that it is a true statement throughout natural number. That is the idea behind. So we have assumed now here that it is true for n is equal to k. So if it is true for n is equal to k, just substitute k in place of what? N here. So we do have p of k now. So p of k is going to be, guys, 6 to the power of k minus 1 is a multiple of 5. You simply substitute k in place of n, guys. You see, nothing is done. P of k is 6 is the power of k, you see, minus 1 is a multiple of 5. I simply put k in place of n. 6 to the power of k minus 1 is a multiple of 5. So here we have to assume that, you see, we have to accept that this is true up to a certain what, students? You see, natural number k, because we are unable to check for every here. Look, I just have tried to check for the first 3. It holds. What about for the first 4? You see, natural number, for instance, if you put 4 here, guys, it holds true. What if I put 10 here? Believe me, it works. 6 is the power of 10 minus 1. A matter of first calculating 6 is the power of 10 and deduct 1 from it. Believe me, you will get that to be a multiple of 5. So as you are doing this way again and again, you see, you will get tired. So instead of doing that, what you need to do is assume it is true up to a certain natural number k. Then if you are able to show that it holds true for the next natural number k plus 1, we can automatically conclude that this holds true for, you see, any sort of natural number. So assume or accept that this is true, or 6 to the power of k minus 1 is a multiple of 5. So as you know, in mathematics, if 1 is a multiple of 5, we can write that as 6k minus 1 equals 5m for some m, an element of natural number, okay? Because it has been assumed that this is a multiple of 5. If it is a multiple of 5, we can write that as 5 times m. For instance, 20 is a multiple of 5. What is the reason behind that? Because 20 can be written as 5 times 4. 30 is a multiple of 5 because 30 can be written as 5 times 6. So if you're considering again that 6 to the power of k minus 1 is a multiple of 5, you can write that as 6 to the power of k minus 1 equals 5 times m. For some m, an element of what? Natural number. So try now to shift this minus 1 to the right, and it turns to be 1 plus 5m. So now, students, you do have 6 to the power of k equals 1 plus 5m. I intentionally wrote this expression in terms of this one, because later, you see, I will try to apply this expression somewhere. Now, look, step 1 is over, step 2 is obtained to be here. Now, we are going to check whether this statement is true for n equals k plus 1 or not. So that is step 3. So comes now step 3. We want to show that this p of n is true for n equals k plus 1. You see? Now we have assumed 2 works up to k. Now we need to check that it also holds true for k plus 1. Now what we need to do is, you see, we directly substitute k plus 1 in place of what? N in your expression. Look, your p of n at the beginning is, you see, obtained to be this one or given to be this one. So we directly put k plus 1 in place of n, and then we will have the here, you see, p of k plus 1. P of k plus 1, and it is obtained to be 6 to the power of k plus 1 minus 1 is a multiple of 5. So beloved ones, here, what we need to show is, you see, this to be true. So if we are able to show that this is true, we are done. We can say that the statement is true. But as you all know, 6 to the power of k plus 1 minus 1 can be written as, you see, 6 times 6 to the power of k minus 1. I intentionally write this in terms of this one because I am on the way to use, you see, what has been assumed here. So beloved ones, what you need to know is, whenever you apply principle of mathematical induction, in order to show the next one, that is the case of n equals k plus 1, try to rewrite, you see, the expression you are having in such a way that you can use what do you have in the case of step 2. So now I'm doing that. Look, 6 to the power of k is 1 plus 5m. Now I just have written this as 6 times 6 to the power of k because I need to use this expression here. You see? So 6 times 6 to the power of k minus 1. Here I wrote 6 to the power of k plus 1 as 6 times 6 to the power of k because the bases are the same. We do have exponent 1 here, so one base can be taken, as you see, and then we can add the exponent. So these two are identical basically. But beloved ones, we know that 6 to the power of k is 1 plus 5m. So in place of 6 to the power of k, you see, 1 plus 5m can be taken because I have arranged that in such a way that, you see, I can use this. So look, 6 into 1 plus 5m minus 1. Now let's simplify this. 6 times 1 makes 6, and 6 minus 1 is 5. So you do have 5 plus 5m. So am I able to take 5 as a common out? Why not? Look, 5 can be taken out, then 1 plus m can come. What is m? M is some sort of what? You see, m is some sort of natural number. The set of natural number is closed under the operation addition. So 1 plus m is going to be another natural number. D, as I wrote here, D is a certain natural number. Now look, this is obtained to be, look here, 6 to the power of k plus 1 minus 1 is obtained to be a multiple of 5, as can be shown here. You see, students? So our intention was to show that this is a multiple of 5. Here we got. You see? Here we got. So this shows you that p of k plus 1 holds true. You see? This implied that p of k plus 1 holds true. So, as you see, p of k plus 1 holds true. Now, let me recall you what principle of mathematical induction talk about. Look, if you do have a statement written like this, involving set of natural number or subset of natural number, we do have certain, you see, steps we need to pass through. So we need to check the case of, you see, we need to check the trueness of this given statement for the first, you see, natural number given here. You see, now it is 1, so we have assured that it holds true. Having this true, what we need to do is we need to go to step 2, and in step 2 we need to assume that this statement is true up to a certain, you see, natural number k, and we did that here. Now we come to what? Step 3, and in step 3 we just have arrived here, and we tried to what? Understand that P of k plus 1 is true. So if this is so, if all these three conditions are satisfied according to the principle of mathematical induction, the statement, which statement, guys? The statement written over here, you see, students, 6 to the power of n minus 1 is a multiple of 5, works true or holds true for whatever natural number n you may take. This is how you can apply principle of mathematical induction, okay?